pharmaceutical purpose, or you can use to enrich the material. So for example, silicon irradiation is one of the things. We do not care about the electricity, production of electricity. It's a very small reaction. But what we do care is the material characterization, where my job is basically. So here is the photo of one of my colleague, Vanessa Peterson, and she look after the neutron diffraction instrument, and it's amazing instrument as well. So again, coming back to the reactor. So you can see the reactor here and the surrounding design. That's the reactor core. And then what you have, you also have a medical irradiation position. So ANSTO provide nuclear medicine to whole region and also overseas as well. So this is one of the very important part ANSTO do is a medical irradiation facility. But we also have a silicon irradiation facility. So we put a very pure silicon in these places, and neutron actually creates the impurity and make it like a semiconductor grade silicon. Now, the chances are the phone you are holding or computer you are using, 9 out of 11 times, the chips which is using inside that mobile or inside that computer, which has the silicon, the semiconductor material which is used in that chips are actually irradiated at ANSTO. So this is again very important work which ANSTO do. And as I mentioned, the other important thing is the material characterization. So we have a number of beam lines coming from the neutron nuclear reactor. So some of this beam line are the thermal beam line, some are the cold beam line, and so on. And I'm going to touch on that a little bit. So basically, what you do, you take a neutron and you pass through this beam lines. Beam lines, in simple terms, it's a highway for neutron. You take this neutron, you bombard on any material you are interested to study, and you have a detector. You can study the scattering profile from that detector and correlate that to the material. I wish life could be that simple, So what we have 15 such instrument at ANSTO. So here you can see this is the reactor. There are some instrument very close to the reactor, and some have a little bit far in neutron guide hole. And this side of instruments are using what we call is a thermal guide. So they use thermal neutron, basically lower wavelength of neutron. And here instrument, they use cold neutron. So the energy of neutron is little bit lower and their wavelength is a little bit higher. And those are used in the mostly soft matter or hard matter characterization. And the instrument which I'm going to talk today mostly is this one, which is called Kookaburra and Kookaburra. So Kookaburra is a small angle neutron scattering instrument. This is the longest instrument in the guide hole. It's from here to here, it's a 40-meter long instrument. SANS instrument has a very high popularity, because the size range which it covers is really nice, 1 nanometer all the way to 500 nanometer. So the demand of SANS instrument is high, and because of that, we had to build the second SANS instrument, which we call Bilby. Now, some of you are wondering why their names are so weird, they are Australian animals' name, except couple of them. So, for example, Spatz is the German instrument. This is the neutron reflectometer instrument which we received and we commissioned at ANSTO. So that's why its name is not Australian name. You can see Sika. Sika is a Taiwanese instrument, and this is basically is built in collaboration with the NSRRC. So that's why its name is not Australian. But if you see the other animal name, and please feel free to Google it, some of these animals are really unique. My favorite is Quokka, not just because I work on that instrument. I will explain you a little bit later. And right now, I use mostly Quokka Kookaburra instrument. Kookaburra is a bird. So I'm going to show you that one. So some of you may have come to ANSTO in past, but this is the top view of our guide hall. And if you come for the like a visit, you might be sitting one of position here, and that gives you really nice overview of our guide hall. This is the Quokka instrument I was talking about. This is 40-meter long instrument, and this is the Bilby instrument here, the another science instrument. Here I'm working with one of my colleague, Elliot Gilbert. Some of you might have known him. And this side of instrument are the thermal instrument. So here, if you see, now that was the overview of the ACNS, which is Australian Centre for Neutron Scattering, where we have all the beamline facility. That's a part of ANSTO, and Australian synchrotron is a part of ANSTO as well, but that's in Melbourne. So I'm not going to cover any X-ray instrument as such, a synchrotron-based X-ray instrument. But here I'm just going to give you rough overview in terms of what is SANS and SAX and USANS in terms of their range. So SANS and SAX instrument are known to cover from 1 nanometer all the way to several hundred nanometer. This morning we have heard this thing before. And USANS actually combine with the SANS and SANS region and extend this length scale all the way to 20 micron. So if you combine SANS with USANS or combine SAX with USAX, you get a very big size range, 1 nanometer all the way to 20 micron. So this is quite impressive. Most of the physical chemistry happens in this size range anyway, right? So that's why it's becoming very very high in demand, both in terms of material characterization, but and also industrial research as well. So if you combine this SANS and USANS, the size range which you get is 1 nanometer all the way to 20 micron. Now, sometimes we just use these numbers very lightly, right? What the size range means. So I'll just give you another visual example. So imagine this is the big ship with a lot of container on it. You are standing on a hill and taking a photo, right? And let's say the size you assign to is 10 micron, okay? Now, take that photo, zoom in that photo. Now you can see a couple of container very nicely. You can see their features and everything very nicely. And that is roughly 250 nanometer, right? Which is the SANS region. Now, zoom it even further, go inside the container and see one box, which is 1 nanometer, right? So this is giving you idea, like combining SANS and USANS give you information at so many multiple length scale that this is a very valuable information, right? So that's basically the size range point of view. But what is I don't know how much you know about the small angle scattering, but I will very briefly just cover the rough idea of the technique itself. So basically what you have a source of X-ray or source of neutron. So source of neutron, as Stuart mentioned, it can be either reactor based or it can be either spallation, and source of X-ray as well. It can be either synchrotron based or the lab based technique. Then you have this radiation going through your sample, either neutron or X-ray. Depending on the interaction with your particle, you're going to get a scattering event. And that scattering event you capture on a 2D detector. So this is the center part of the detector, and going outwards give you the scattering vector Q. So this scattering vector Q and the intensity, you can convert into one-dimensional profile, right? The common rule is, the small, if you have a large distance or the bigger particle, they generally scatter at a smaller angle, which is correspond to the smaller Q value. So this is like an inverse space technique, and this is actually. I would say it's a beauty of the technique, but sometimes it's also creates some challenges. The other thing is, if you can do things with X-ray, why to use neutron, right? So there is nothing wrong. You can use X-ray, you can use neutron. Both has their advantage and limitation. So for example, if you using X-ray, X-rays are generally high intensity. Even lab-based X-ray source could be very high intense. So it's good thing. They are fast. Generally measurement don't take longer time in terms of small angle X-ray scattering. Maybe if you are using synchrotron based technique, maybe 1 second, 2 seconds per measurement. Even if you are using lab based technique, maybe 20 minutes to 40 minutes and done. And they are local. So for example, you can buy small angle X-ray scattering instrument, install in your lab, and that's it, right? The problem limitation, which I would say, is the contrast issue. There are techniques in X-ray, where anomalous small angle X-ray scattering, where you can play with contrast a little bit, but not much. On the other side, neutron provide you this ability of contrast. So Stuart actually mentioned in one of his slide about the neutron cross section and how it actually helps in terms of contrast information. I'm going to show that a little bit more. So neutron provides contrast option or the labeling option. You can chemically you can have a same material, just a different label, and that helps in terms of neutron scattering. The only limitation I would say is a limited availability. As Stuart mentioned, there are not that many neutron scattering instruments around the world. And also, like for example, spallation based technique or the reactor based technique, you always, struggle in terms of getting beam time and so on. So availability is always limited. But anyway, this is what we are doing. We are trying to create a demand so that we can have more facilities, and so that science can progress further. So in very layman terms, I would say small angle X-ray scattering is like a black and white TV. If you are young enough to know what is black and white TV is, or old enough to know what is black and white TV. But neutron is like a color TV. Okay. So now coming back to again this 2D scattering profile, you convert this 2D scattering profile into one dimension, and basically you can plot the intensity on the detector versus this scattering vector Q. And what you get this really nice Q versus intensity. Now, if you remember, I mentioned it's an inverse space technique. So basically Q is the higher Q will give you the smaller particle, smaller length scale information, and the low Q can give you the information of the larger particles. So for example, if you are interested only in the structure of one aggregation, for example, molecular aggregation, at high Q, you can get the information about the internal structure of that material. And if you go to the low Q at different length scale, you can get the overall information about that structure of that material as well. So this is the very rough conversion, and how your scattering profile look, where you have a features will tell a lot about your material, or tells a lot about the scattering length of your material, or the contrast of your material, and so on. Now, again, coming back to the same slide of the SANS-X and USENS in terms of the range, what I want to show you the real life small angle scattering example. So this is the SANS profile. So this is done on the Kookaburra instrument, which is the SANS instrument I'm going to talk about today. And here is 1 nanometer, and if you see the last point here, it's roughly 500 nanometer. If you convert based on the D is equal to 2 pi by Q. So this range is really impressive. Not that many small angle neutron scattering instrument in the world which can go up to that far into low Q. So that is impressive itself, but you can combine that with USENS. So USENS provide information from 100 nanometer or depending on, how quickly your sample hits the background, 100 nanometer all the way to 20 micron. So if you combine this, it's amazing bigger Q range. So when I teach student, I say, imagine you are looking through a keyhole, and this is a big room. There are a lot of elephant inside the room, but because all the elephants are standing very close to your keyhole, the only thing you can resolve is like their small features, for example, trunk, ear, or legs, and so on. But you can't confidently say those are elephant, or those are small babies, or the big babies. The only thing you are seeing is the small feature and the scattering coming from their scheme, which is the interface, right? But now you take this keyhole and go on to the other side of room, which is the ultra small angle neutron scattering. Now you can see whole bunch of elephant. You can say, okay, what is their volume fraction in terms of numbers? You can see who is smaller, who is bigger, but probably that's too far to see the smaller feature. So by having this combination of sans and U-sans, you can resolve the structure at all the length scale in a one go. So that's the beauty. Now more and more papers are coming out which combine these two techniques and give you this information. So that's the sans and U-sans combined. But in general, what I want to tell you also, the comparison of X-ray and neutron, the one thing which neutron have is the interaction with the nucleus, right? So if you remember that big stadium analogy, so in any molecule, two nucleus are separated by certain distance, right? So in the same length scale, if I'm talking, so you take any molecule, the separation between the two nucleus is quite lot if you see from the eye of neutron. So in the length scale of that stadium, it's a 1 kilometer separated, right? So in any molecule, the two nucleus are separated.
Go ahead.
Okay, sorry. So in any molecule, two nucleus are separated by certain distance. Let's say this is a 1 kilometer distance, right? And what you are trying to do, you are trying to hit those nucleus which are separated by 1 kilometer by using this piece, which is the size of neutron. So what happens when you bombard this neutron to a nucleus which are so separated is most of the time nothing, right? Everything goes through because there is a lot of empty space. You get some scattering event, and we are interested in those scattering events. And the other advantage of neutron is, because of their wavelength nature, they can provide you information at atomic or molecular length scale and so on. But the biggest advantage which I see is the cross-section, how they interact with the isotopes. So for example, if you see X-ray, for X-ray, hydrogen and deuterium, which is just an isotope, they are same. And basically, it's a boring profile. So if you go higher in atomic number, the electron cloud increase, and your interaction X-ray cross section gonna increase. But for neutron, hydrogen is very different from deuterium, and this is what we take as a advantage, because what we can do, most of the system which we study in, let's say, aqueous medium, it's not limited to aqueous medium, but let's say you are studying any system in aqueous medium, you can mix H2O and D2O, which is chemically same. But for neutron, it's huge difference. And by doing that, you can do contrast match experiment. And I'm going to explain a little bit more on the contrast match experiment later. The other benefit, you already heard this, that it's actually non-destructive, and it is very high, has a high penetration. So you can put whole engine there, whole big piece of metal or big sample environment, and neutron can go through. And the reason it can go through, you remember that lot of empty space, So if you put something big, looks like a bulky, completely impossible with X-ray, neutron is fine, right? It can go through that, and you can have with or without sample, and the difference between this gives you the information about what is the structure within your sample. But as I mentioned, the biggest advantage is the contrast variation. Now, what is contrast variation? So as I said, let's take the example of aqueous system, but this is again not limited to the aqueous system. Even if you work in the hard matter area, there are examples where you can change the contrast of material by by using the by using the labeled atom in your material, and that will provide you the contrast. So basically, I'm just giving you example with H2O D2O because it's a very versatile and has been used a lot. So you can see the scattering, how neutron react with the H2O and D2O. So scattering length density for H2O is in minus 0.56, 10 to minus 6, whereas with D2O it's 6.3, 10 to minus 6, right? So it's huge difference. And if you can combine H2O, D2O, chemically same, you can match any component. So if you are working with multi-component system, or even if you are interested in the one part of your molecule, but not the other part of your molecule, you can contrast match that one thing out and study this. Now, again, sometimes it's very hard to comprehend what is contrast match. So I'm just putting a visual example here. So in this test tube, I have a 3 component, 2 glass component and the solvent. So because the glass refractive index of the 2 glass component is very different from the solvent, what happened? You can see just a mess, right? However, if I somehow change the refractive index of that liquid to match the refractive index to the first glass component, which is the glass wool, I can now suddenly see the second glass component within that mixture. There is still the glass wool around that. It's just that because it has the same refractive index, we can't see it. So that is exactly what we do in the contrast variation. So for example, if I am interested in something like a core shell particle, then having a contrast different from this both core and shell, I can see all 3 components. But if I match the contrast to the shell part, I can only see the core. Or if I can match the contrast with the core, I can only see the shell. And by doing that, or by doing this structure analysis, we get so much information. For example, one of the research which we did is the solubilization of the drug molecule within the drug carrier. Now, drug carrier is a surfactant. It forms the core shell micelles. So we were not sure where actually this drug partition. Does it partition in the core or does it partition in shell? So by doing this kind of contrast variation, we can locate where the molecules are, The other thing I want to mention is at ANSTO, we also have a national deuteration facility. So national deuteration facility is really cool because what it provides you the ability to deuterate your molecule. So let's say if it is not available, in market and you want to deuterate any molecule, we have both chemical deuteration and biodeuteration. So there could be a completely separate presentation on deuteration part, how we actually deuterate molecules and so on. But if you are applying to the beam time at ANSTO, and if you really need deuterated molecule, we can always talk to the National Deuteration Facility people, and they are more than happy to help. So now that's the basic part finished. I'm going to go on to the SANS instrumentation. So here, as I mentioned, we have a 2 SANS instrument. One is a Quokka, 40-meter long instrument, and very similar instrument, Bilby. This is the pinhole instrument, and this is the time of flight instrument. The other instrument which we have is the Kookaburra, which is a USANS instrument. It's very different design than this, and I'm going to talk a little bit on that. And then we also have a Bruker instrument, which is a small angle X-ray scattering instrument, lab-based instrument. This is the quokka animal, by the way. This is the most cutest animal. I personally find it more cutest animal. If you ever get chance to go to Western Australia, go to Rottnest Island, and you will find quokka there. We are replacing the SAX instrument now. We are getting a very new, really nice the SAX instrument, which also have the USAX capability. So when you apply for the beam time for any instrument, you can combine multiple instruments for a one research problem. Okay. So far so good. So now I'm going to go and explain a little bit about the Kookaburra instrument. So Kookaburra is a small angle neutron scattering instrument. It's a pinhole instrument. Although the size of the beam which we generally use, is 12.5 mm diameter, but we call it pinhole instrument. And this is located on the cold guide 1. So it uses the neutron from the cold guide. We have a 20-liter liquid deuterium cold source. It's generally the temperature of the cold source is 20 Kelvin. So we liquefy deuterium. Neutrons interacts with it and lose the energy and change the wavelength, and we use those wavelength for the cold instrument. The Q range which we get from the Kookaburra is 6×10⁻⁴, all the way to 0.7 or even bigger if we modify the instrument a little bit in terms of the velocity selector. It used the focusing optics. So using the focusing optics, you get this amazing, impressive Q range. The flux which you can get with Kookaburra is really impressive, 2 to 10⁷ neutron per centimeter squared per second. And we use the velocity selector. Now, what is velocity selector? Velocity selector because it's a monochromatic instrument, when you have neutrons coming from the cold source, it has all sorts of wavelength. So this fast rotating turbine actually helps us to select one wavelength. So that's why it's a monochromatic instrument. And I'm going to show you one animation which will explain this one. And then we have a state-of-the-art 1 meter by 1 meter detector with 5 pixel. So Kookaburra is a really impressive instrument, and it's very versatile, has been used in number of different areas, and I'm going to talk a little bit about that as well. If you are interested more about this instrument, please feel free to read this paper, and always more than welcome to contact any of us. We are very friendly people, and we can always help you with your quest. So here is the Kookaburra instrument. So as I mentioned, this is the neutron guide looking at the cold source. So you have a nice polychromatic beam coming. It going through this fast rotating turbine, which just has different blades and a neutron absorbing blade. So basically, neutron is a particle, so it blocks any fast moving neutron or any slow moving neutron. It only allows one speed of neutron to go through. One speed of neutron is equal to one energy of neutron, which is equal to one wavelength. So the wavelength spread which we get from the velocity selector is roughly 10%. Then it goes to the number of this collimation system. Either you can use guide or collimated beam. And then it goes to the sample area where you can load your sample. Now, depending on what you have in your sample and how it's going to interact with neutron, you will get a scattering event. And we capture this scattering event on this 1 meter by 1 meter detector. Now, this scattering event, as before, as I mentioned, it's a 2D detector. So you get a direct beam, which we prevent so that we don't burn out our detector, and then the rings around it. So basically, you can put detector very close to your sample, or you can push very far at the back. So when you push far at the back, basically, you get information of the large structure. Now, that is the small angle neutron scattering instrument, right? So that provides information from 1 nanometer all the way to 500 nanometer. What if you want information even at larger length scale? We can't build instrument 100 meter long, right? It's not practical. So the USense instrument which we have, a Kookaburra, is work on the Bond's heart principle. It's a different way of measuring the signals. So basically, what you have a neutron coming from the reactor, from the cold guide. Then you have a nice pre-monochromator which sends neutron to this crystal. They are channel cut monochromator crystal, and then we have a 5 bounce on them. So neutron bounce 5 times, then it goes to the sample area, then it bounce again, and then it goes to the main beam. Whatever it can't bounce goes into transmission detector. That's a very simple layout of the USense instrument. And as I mentioned, this is used for structure characterization from 100 nanometer all the way to 20 micron. And similar to SANS, is a very versatile instrument. It is used in all sorts of area. So people have studied minerals and rocks and porosity, cracks within those material. Cement and concrete is a really important area which you can use USANS and SANS. Lot of soft matter, so polymer, hydrogel, or the proteins, all kind of macromolecular assemblies you can study with SANS and USANS. And magnetic material. This is becoming really popular with the SANS and USANS. The SANS instrument which we have a capability of polarization as well. So if you are interested in polarizing neutron scattering, small angle neutron scattering, you can always contact us, the USANS which we have has a two option. Either you can use for the high flux mode, or you can use for the high resolution mode. So these two modes are really important. We use this all the time, and I'm going to explain a little bit what these two modes are. And it's provide really good complementary to our both SANS instrument, but it can always use by itself. So for example, if you have some particle which is from somewhere between 100 nanometer to 20 micron, you do not have to use SANS instrument. You whatever you want to do, you can just get information from USANS. Okay, so now coming back to what I was trying to mention about the two mode, high intensity mode and the high resolution mode. So Kookaburra have this. If I go back, I want to show you this turntable. So this is the turntable. We have this two turntable. One is called the the monochromatic turntable, and this is the analyzer turntable. So, and this is the sample area. In each turntable, we have two sets of crystal. One is silicon 311 and silicon 111. Silicon 111 is for the longer wavelength, and silicon 311 for the shorter wavelength. One is used for the high intensity, other uses for high resolution. So if you rotate this table 180 degree, you can use one over the other. And the reason to do that is because we get so many different kind of material to study using this SANS, study using USANS. Sometime if you are interested to study pores or the cracks in the rock or even the structure within the mineral, you have the one problem which very hard to believe is the lot of scattering. So even if you put a very thin sample, sometimes you get so much scattering, which is not good, because what ideally you want one neutron scatters and then directly goes to the detector without scattering again. If it scatters again, then it is creating problem of multiple scattering. So ideally, we only like, up to 10% scattering, not more than that, because it might then have a problem of multiple scattering. So multiple scattering decrease with if you use the lower wavelength. That's why we have this two mode. And to explain this instrument, I would say, this is like a periscope. So if you are shining a light from here, and if I'm standing here, so basically this becomes like a periscope and I can see light if these two mirrors are perfectly aligned. We have like a rocking curve on this mirror. We have rocking curve on both crystal, but for the normal operation, we only rock this crystal. And when we rock it, so we go from the negative angle to the zero angle and then positive angle. So when we rock it, now this is the beauty of USANS instrument. This rocking is so precise. We actually measure 1,000th part of 1 degree at one time. So you collecting scattering at each angle of this rotation. So what happens if you don't have a sample here, and this is like a periscope? So basically what happened, the intensity will go up and then it will fall down, right? If you do the rocking curve. But if you have a sample which is a scattering, then what happens? If you do the rocking curve, your intensity will still go up. It will fall down, but the falling down rate is a different, and it may not fall down as steeply as for the empty position. So basically, you take the difference between these two scattering profile at each angle and convert that into the Q value. So I'm going to explain that in the next slide, in the slide after. But basically, high intensity mode has a very high flux compared to the high resolution mode. And they have a slightly different Q value you can achieve. So if you are interested even smaller Q value, you would use high resolution mode, but if you have a less material which going to scatter, then you can use the high intensity mode. So if you remember that rocking curve I was mentioning, so if you plot into the log scale, it won't look like a peak, but it will look like this one. So you have a basically, nice empty fall down. And if you put the sample, you still have this direct beam, but the fall down is not the same, but different. So this is nice this is a nice polymer particle, and you can see because they are monodisperse, you can see these nice features coming. These are the different size of the particle, and you can convert this one into the Q value versus intensity and subtract this and get a really nice scattering profile. And now many of experiment, as I mentioned before, actually combines that with the SANS, which is on this length scale, and it gives you this very huge Q range. This is our sample environment. This is the one environment which we use most. This is called the 6-position rotating temperature control tumbler. So for example, when you are studying material with the U-sense, basically what you have a matter which is settling down. Let's say if you are studying aqueous system. So what you want to do, you want to actually rotate them in the beam. So this is the perpendicular to the beam, and then that way you can have a nice homogeneous mixture. But as I said, these techniques are versatile. So here is another example where we have a rheometer. So a lot of food system, polymer system, hydrogel system, where people want to see the shear profile, shear effect on the structure. So you can do that in situ mode. If you are into magnetism, we can also put magnets on SANS and U-sense, and you can see how the structure are changing when you are applying the magnetic field. So that was just an overview of SANS and U-sense instrument. I can talk about each individual instrument for hours and hours, but that was just a brief overview. Now I'm going to show you like what we can do with the SAS and also some of the sample environment. I think that's a very important thing, because if you can see, how versatile sample environment we have, it kind of helps you. So here what we have, you can use this technique to study various material. As I mentioned about the U-sense, it applies for the both SANS and U-sense and even small angle X-ray scattering. And what kind of information you can get? So you can get information about the size of the scattering particle. So this scattering object could be anything. So for example, aggregation of surfactant, or the pore size in the mineral. Or let's say, we saw the example of the this catalyst with the size of those rings. You can study those one. We do a lot of research on battery material, so you can have electrodes. You can see and study the dendrite formation, which is quite big challenge in the battery research these days. So we already done the experiment there. Watch this space, you will see really nice paper coming from that. So not only you get the size information about that scattering object, but the shape of those particles as well. And then what other information you get from the scattering? I tell this to many people, that scattering profile is just like a black box. You can extract as much information as you need, or as little information as you need, or as much information as you want. It's so much information hidden in that scattering information profile. You can also get the interaction. So for example, if particles are very close by, or if they have a charge interaction, it's going to show up in the scattering profile. So you can get that information as well. And as I mentioned, the most benefit is, you can study molecules or their system in most relevant conditions. So we do lots of in situ measurement. Recently, we did a very nice experiment of in situ digestion of the yogurt and cheese, how this get digested and broken down and so on. You can use those in situ digestion kind of setup and so on. So my next slide, which I'm going to show you, the sample environment, might give you the idea like what kind of science we can do using the small angle scattering. So on the SANS instrument or USENS instrument, this can apply to both SANS and USENS instrument, okay? So the most common sample environment which we use is called multi-sample changer. So basically you come to do experiment, you prepare all the samples, we load them in the sample holders. You can load this sample holder in this multi-sample changer. It is temperature control, so it can go from -40 to 120 degrees C, the most common one. So you can load up to 20 sample at a time, and everything is automatic. So you don't have to worry about, what detector distance we're going to use, what we're going to do. As long as you have some idea about your system, that this is the size range we are interested and so on, you can use everything in automation mode. So you load this 20 sample and it press the button and it goes, we have a different type of multi-changer. One is the common 120 position, but we also have a 10 position which can go to higher temperature, even more than 250 degrees C. We also have a new type of sample changer, which is with the 12 position, and each position is individually temperature controlled. So for example, you have a very sensitive sample and you say, look, 5 sample I want to heat up to 60 degree, but remaining sample I don't want to heat them. I want to keep them at 25. You can do that very easily with this 12 position multi-sample changer. So those are for the sample which you can load and study. Many times, this is the very big chunk of our measurements. We also, as I mentioned, we also have a various magnets. So we can go up to 11 Tesla field, and temperature as low as less than 1 Kelvin. So it's very impressive. You can put the whole magnet on SANS and USENS and study material in the magnetic field. If you are interested in the kinetic kind of study and you need to mix 2 or more sample and study the kinetic information of that material. For example, how 2 proteins are actually mixing with each other. You can use the Stokes flow measurement, and do the time-dependent kinetic kind of study using the SANS instrument. I showed you the rheometer. You can put rheometer on SANS and you stand and actually study the material while applying the shear to those materials. So that's the rheo setup. I have published a couple of papers on that, and it's really cool. And you have seen that rotating tumbler. So basically, when you apply, when you want to actually, if anything is settling in the beam, phase separating, it's not good. You want a homogeneous, so you can actually have a rotating kind of sample environment and study that. These are a couple of examples of our sample holders. So for example, here is the very common benzo cell. You can load sample. This is the 1 millimeter all the way to 10 millimeter path length, whatever you want, and take sample as less than as 300 microliter and so on. If your sample can't be put in this one, you can actually use something like that, like a demountable cell. And we also have a lot of custom made holders. So for example, if you are interested in films or metal films or something, you can just stick in front here, right? And this is a demountable cell. So it's like a 2 glass slide, quartz slide, and you can load your sample between this glass slide. So this goes into that 20 position or 10 position or 10 position sample holder. Then we also have what we have is called the rapid heat quench cell. So rapid heat quench cell, if you want to apply the thermal shock to your sample, we can do that. We have a rapid visco analyzer. This is very common in food science or food manufacturing, where people use the viscosity kind of measurement. We also have a high pressure SANS cell. So high pressure SANS cell is awesome because it can go up to 350 megapascal pressure. One of the experiment which I did where the researcher wanted to study how they can apply pressure for the recycling plastic. This is the plastic with the two segments, and we wanted to see if we can apply the pressure and mix this two segment within each other. And this is a very cool experiment. The data are not published yet, but will soon get published. And then what we also have a one in the world, which is the in situ differential scanning calorimetry instrument. So if you are interested in the thermal profile of any material while you are collecting small angle neutron scattering, you can do that. So these are some of the sample environment I have listed. We always expand more, and we have a dedicated sample environment department. You can actually visit our website and get the full catalog. Like, we have a catalog which shows all kind of different sample environment we have. If you need any information, please do not hesitate to contact me. I'm more than happy to take any inquiries. So this is the sample environment. Now, I will show you this basic equation. I don't want to bore you, but before I go on to the example, which I want to show you today, I thought I'll give you this one equation. Believe me, there are lots of equations in small angle scattering, but I'm just going to give you this example. So what this is saying, it's saying the intensity is proportional to the contrast square times P of Q, which is a form factor, and the S of Q, which is a structure factor. So basically, the intensity which you see here is a result of form factor, so shape of the size of the particle, but maybe also the interaction. If there is a particle are very close to each other, or if they have a charge interaction, you can get them. Scattering is also affected by the structure factor, and the contrast is the huge thing, right? If you don't have a contrast, if your solvent and if the particle you want to study have a same or similar scattering length density, then your intensity will be nothing. It will be like this. You can't see the glass rod in the liquid which has the same refractive index. So this is the equation is very important. Whenever you want to submit a proposal or want to study something, think about all this particle. Okay. So that was the rough overview about the small angle scattering. Now, what I'm going to do, I'm going to show you one example where I have used SANS and USANS. I have a lot of example, but I picked this example because this is really example and suits very well with this conference. So, in this example, what we have done, we have used silk-based hydrogel. So silk is very common material, like a very natural material. And we have made silk-based hydrogel for the biomedical application. And then we have used SANS, which is Koka instrument, and Kookaburra instrument to study this, this material. And I'm going to show you some really nice data from that one. So just to give you this overview, this is a collaborative work and mostly done by the NABA and Namita's group, and I have been collaborating with them since 2014, and we have published more than 10 papers on this area, and it is one of the highly cited research. So if you are interested, I can always send you the paper for this one. So in this work, what we have done, we have made the hydrogel from the silk and combining silk with two other molecule. One is the protein molecule and one is the polymer molecule. And we have used not only SANS and USANS, but we also use the small angle X-ray scattering to study this. And I'm going to show you that one, why we did that. So silk is very abundant in nature, It has a high mechanical strength. Silk is one of the strongest material known, and it has excellent biocompatibility. So that's easy to extract, from the different source and so on. And the thing is, it can form the composite with other material and actually even improve the property. So silk has some limitations somewhere, and you can improve this property more. So in our research, what was the motivation? So in our research, what we wanted to do is we wanted to make a hydrogel for the tissue repair kind of application. So basically, you make some hydrogel. Either you cross-link that hydrogel, gel by using photo or, like a chemical cross-linking. And basically you can repair the tissue, and that would have a high biocompatibility. So Naba and Namita have been publishing a lot with this kind of molecules, both silk and other molecules. So what we did, we took the silk and we mixed with the photo initiators and other compound which can use light and make the hydrogel possible. And basically we form the hydrogel, and you can see the hydrogel as the nice SEM image here from the hydrogel. And what you can see from the surface that there are these large pores, and roughly pore size is 2 micron or something like that. These pores are very important because that allows blood or body fluid or the liquid to go through and provide that porosity of the material. But silk, as I said, it has some limitations. So what we wanted to do, we wanted to actually improve the silk. And to do this, you can actually mix silk with the other protein, or you can actually mix with the other polymer. And that is what we did. So we not only study the silk hydrogel made out of the silk, but we actually combine this silk with other molecules. So one of that other molecule is called REC1 resilin. So resilin is really common elastic protein. It's again disorder protein, and it is found in like insect, So here is the one example where that protein is found. So we actually genetically modified that protein and only took the one component out of it. And this protein is awesome because if you see, it has a really high fatigue life cycle, and it's very resilient. So you can mix this resilin with the silk and make a new compound. Or you can take a completely man-made polymer, like this is the PVC, polyvinyl caprolactam, very commonly studied in science, and it is really thermoresponsive. So if your application requires very thermal kind of based thing, you can actually use this one. So silk is so versatile, it can actually combine with resilin or this polymer and make a different hydrogel. And that is what we did. We made this material, 2 different kind of material by using this 3 combination. Now, this is the example how you study it. So to do a proper study, you want to study each individual component in their form as well, in solution form. So here is the example where we studied not only silk, resilin itself, and the polymer itself in the solution. And you can see the behavior, the scattering, what information you can get from the scattering. So not only you can see their size information, but also what kind of orientation they have. So we just studying the normal SANS data of this 3 component, we know that they are like a Gaussian chain kind of structure, fully swollen in the solution. This is a very simple analysis. It does not take a lot of time, and it gives you such a valuable information from this one. We also thought, okay, what happened if we increase the concentration of this material? So in previous example, the silk was only used 2%. We thought, okay, what happened if we actually increase the concentration even more? Because silk is known to form aggregates by itself. It's not very stable in a way in solution. So we went up to the 15% concentration. And the slope at high Q was still close to -2, which is the example, which is the representation of like a Gaussian coil structure. So even in solution, there was some aggregates. See how good information it's the scattering giving you, but also it's telling you, like, apart from those small aggregates, it's a mixed system. Most of the protein is still staying as a Gaussian chain. Okay. Now we did what the photo cross-linking and everything, and what happened suddenly. So this graph shows you the gel made out of the silk. Okay, so now you see that -2 slope suddenly changed to -4. And this is SANS and USANS data combined. That's why it's a 4 order of magnitude bigger, right? So at high Q, where the information comes from 1 nanometer to 5 nanometer, you can see it's went from the like a Gaussian coil to more sharp interface, sharp boundary. So that's a very good example to show you like what happening at nanometer length scale. Then we have something called Gunnier region, nice Gunnier region, and then we also have some profile at a U-sense region, which is a micron length scale. And if we plot this graph little bit different way, which is called Kratky way, you can assign these peaks to a different domain within the structure. So we say this is the coming from hydrophobic domain. And how do we know? We know based on the lot of other study which we have done. So this is another lesson in neutron scattering or X-ray scattering. You need to have a lot of information about your system in order to actually use the SANS and U-sense so that it can give you the full picture. It's a very specialized technique, okay? It also gives you information about hydrophobic domain. I'm going to show you in next slide. And then you remember those pores which are very useful. So that is the pore structure here. So now in this slide, as I mentioned, we made two different kind of gels. One is combine the silk with the REC1 resilient, and then combine silk with the PVCl. So here is the PVCl, whereas here is the silk versus silk and REC1. And this shows like by mixing the resilient, what happens? Suddenly, your porous structure folds down. There is less porosity. The hydrophobic region is increasing, and the hydrophobic philic region does not change that much. Whereas it's a different scenario here. And we converted that into our hypothesis, and it was published, and you can see the internal structure like a domain, which is the hydrophobic region. Then you see the separation between this, which is the hydrophilic region. And on the bigger side, the keyhole on the other side of room, which gives you the information about the pores. So what happening to the pores? Are they becoming smaller or they becoming bigger, and so on? So this work was really good. And this is just a small example. We published so many papers using silk with the graphene oxide for the printing application, like a solar application, solar cell application. We made the silk with the soy protein and made a gel out of it for the, again, 3D printing of the tissues and so on. So we have published, and all this information available on my Google Scholar profile. If you are interested, or always feel free to contact me. And this material is really awesome. It's a really good example how the material science is changing the world, using a very biocompatible material, easy to process material, and making them very specialized. So conclusion of that study is we can study a lot of things using SANS and U-sense, and get information at a very large scale structure and so on. So before I finish, I just want to give you a take-home message, So small angle scattering is a very powerful technique. It gives you information from 1 nanometer to 20 micron length scale. And if you play with the contrast by either doing an isotope replacement or using mixture of hydrogenated and deuterated solvent, you can actually push the limit even further by understanding different part of molecule or different component of one systems and so on. And it, as I mentioned, it provides you information about not only the form factor, but also the structure factor. So if you are interested in the interaction, for example, you are interested in magnetic particle where you have a domain boundaries or something, you can use the SANS and U-sense technique, okay? And if you are interested applying beam time, it's a government facility, so you have to apply for the beam time. Each instruments are really specialized instrument, right? So I'll give you example on the SANS instrument, which is Kookaburra. To run Kookaburra for a day, it cost Australian government 10,000 Australian dollar, So there is a huge money invested by Australian government. The only thing they want is, like a very good science coming out of this instrument. So if you have a really nice science, or if you are thinking to use this, or come to Sydney, I would love to welcome you. We have 2 proposal rounds every year, generally 15th of March and 15th of September. The next proposal round is not in 15th March, it is on 15th of February. So it's still a little bit of time, but don't wait till the last moment. If you want to submit something, let's start ball rolling. Discuss with me. It's only 2-page of proposal, but we need to make sure it's a very competitive. The success rate is very low, and COVID actually made the situation worse. On SANS and USANS instrument, the success rate is in 25% mark. So we rejecting 75% of proposal. Hopefully this statistic will improve. We want 50% success rate at least. But COVID made life a little bit difficult. So if you are interested, if you want to submit proposal, please do contact me. And if I can't help you, I'm sure I will find other. So I only showed you the SANS and USANS instrument today, but as I mentioned, we have a 15 different instrument, not diffraction instrument, inelastic neutron scattering, and so on. So if I can't help you there, I can always redirect you to one of my colleagues. By saying that, I finish my talk here, and I really like to thank all of you, for your kind attention today. Thank you.